All right, so welcome back. So again, this is a statistics class, and as we hopefully I convinced you last time, probability is an essential part of statistics. We have on the one hand the truth, a stochastic process, a data generating process that is generating what the observations that we see, and on the other hand we have just partial observations of it. And probability tells us how to given the truth, what the observation would look like. And statistics is reverse engineering this process, starting from observations, trying to infer what is the data generating process. And so for that, we need to know a little bit of probability. Hopefully, you've looked a little bit at the questions that I asked you. Now, probability is a very vast field. I personally like to think that all of probability is relevant to statistics and machine learning. So if you feel like you're a little rusty, I really encourage you to go back and open a probability book. But there's also some online versions of probability classes that you can take a look at. But just to make sure that we put the spotlight on what will be relevant to this class, we'll just spend one lecture taking a look at the probability issues that are relevant to us. Okay, so as I said, the thing that arises a lot in statistics and most of the time are averages. Okay, we replace expectation by averages. And the thing that justifies us from doing this thing that says that expectations are close to averages or averages are close to expectations, I guess, is this law of large numbers. Okay, so if you look at the law of large number right here, so there's two versions. There's the weak version and the strong version. And what they essentially say is that if you take the average of random variables x1 to xn, all right, so last time we saw that we will typically denote this quantity by xn bar, then they're converging to this quantity mu, which is the expectation of each of those guys, all right? So their IID, x1, xn, have the same distribution in particular. Being independent is very important for them to, for this theorem to hold. But what's important is that all those guys have the same expectation, and it's denoted by mu. And so the average converges to the expectation. The difference between the weak version and the strong version, we'll come back to it, is the sense in which this convergence happens. So you have a convergence of a random variable to some deterministic number, and this can happen in several ways. And the two ways that exist, the weak version says that this happens in probability, and the strong version says that it happens almost surely. The second one subsumes the first one. So if it holds almost surely, we'll see that it also happens in probability. So that's the first thing. It says that if you have a large enough sample size, if n is large enough, then you should be close, right? That's what limit means. Now, how close, this does not tell us anything. Okay, so in particular, if I have my xn bar that converges to mu, as n goes to infinity, oh, what's wrong with this chart? All right, so as n goes to infinity, it could be that xn bar minus mu is something like 1 over log of log of log of n. Okay, so this is not very useful because it means that for a given n, like let's say n is 10 to the 10 to the 10, then this thing is basically 1 over 10, and this is not helping at all. This is extremely slow. But this cannot be ruled out by the law of large numbers. So we need a more quantitative way to say that, OK, maybe for a given finite sample size, what can we say? And this is essentially what's telling us the deviations of xn bar, the typical size of the deviations of xn bar around mu. Okay, so xn bar will be not exactly equal to mu. It will have some inherent distinction. And the central limit theorem tells us that if you take xn bar and remove mu, divide by sigma, which is the standard deviation of x, and then you multiply everything by square root of n, then this thing converges to a Gaussian. There's many ways to view this problem, to view this result, right? So you could just say, OK, if I just apply some operations to xn bar, if I sort of rescale it properly and center it properly, then I have convergence to a Gaussian. And we will mostly use this result as such. But what's happening is the important part, what the message, the quantitative message is telling us is that if I say that xn bar minus mu over sigma is about equal to some Gaussian, okay? a standard Gaussian, if you draw a standard Gaussian with a high probability, you're going to get a number which is between -3 and 3, okay, with like overwhelming probability, almost probability 1, which means that this quantity, sorry, square root of n, which means that this quantity will be a number between -3 and 3 with overwhelming probability. Which means that if I look now at xn bar minus mu, it's going to be less than 3 times sigma over square root of n with overwhelming probability. So now this is giving us something which is much more interesting. It's actually telling us that if I look at xn bar and I see how far it is from mu, I don't actually see 1 over log n. I actually see 1 over square root of n. Okay, so that's the thing that matters in this result. Now, the role of the Gaussian will allow us to be extremely precise about the constant that we get. And the constant 3 did not appear in the conversation we just had, right? I just told you something about this 1 over square root of n. And so if you had something different here, that would not affect the discussion, the qualitative discussion that we just had. But this constant 3, we're going to get much more precise numbers because I said, well, with overwhelming probability. Well, if you don't want to be overwhelmed, you just want to be whelmed. Okay, maybe you just want this probability to be 95%, then you can pick a better number than 3. Okay, so that's basically how those things are going to be working. But really, the essence of this result is that this thing is a random variable. Sure, it can take numbers that are completely unbounded, but we know that somehow this thing is, say, stochastically bounded in the sense that with high probability, this thing does not go too far. This thing is something which is of order of a constant. That's what's important. Okay, so that's the central limit theorem. One thing that you need to be a little careful is that here I actually hid the fact that this is approximately equal. And I'm sort of cheating you a little bit because it could be that the difference between the two quantities is actually of order 1 over log n. And that would actually take us back to square 1, but it's not the case. So there's something called various n bounds that guarantee that this thing is actually happening at a certain rate. Okay, we're not going to go into such details. This convergence here is a new type of convergence, and those are the 3 types of convergence we'll see in probability, almost surely, and this one happens in distribution. We'll come back to this. Who has never seen the central limit theorem before? All right, thank you. I actually wanted to ask the opposite question, but thanks for doing this. So we will see how we manipulate this thing. At this point, all you need to know is this thing. We're not going to see the proof. We're not going to bother with it, but that's essentially the most important aspect of the central limit theorem. So just that things properly rescaled converge to some Gaussian. The most important part is how to use it. This is not a probability class. But again, I encourage you to take a look at it. There's some simulations that illustrate it that are quite illuminating. So what if n is not large? Oh, by the way, let's come back to this. I just wanted to give you a rule of thumb to apply the central limit theorem, right? When is it true that this thing is approximately equal to that, right? This is, again, there's some convergence result that's happening here as n goes to infinity. And so what is n close to infinity? Well, for this class, the rule of thumb will be n larger than or equal to 30. Okay? So of course, those numbers depend on how sure you want to be about your results. If you were, if this was a life and death situation, you might want to go to n larger than 50. But n larger than 30 will be fine enough for the purpose of this class.